Okay, this week we are going to look at what is called generating functions. Before going into the details, let us look at something related to it, which is what we call counting sequences. So, what is a counting sequence? A counting sequence. So, suppose you have, let us say that you have a combinatorial class of objects, say permutations or triangulations of a polygon uh, or binary words of length, and or the set of all binary words, for example. Now, if you consider these classes, let us say that we are looking at binary words. Then we can say that W is the set of all binary words, where W consists of the empty words. Then you have 0, you have 1, then you have 0, 0, 1, 0, 1, 1, 0, 1, right? So this way you have this set of all binary words. Now, if you consider such a class of combinatorial objects, then you can talk about the size of an object to be. We can define whatever we want. For example, I say that the size of a binary word is the length, right? Number of zeros and ones inside, right? So if I define it like that, then for every natural number, we have a corresponding subset of W, and this the cardinality of this subset, let us say, denoted by Wn, right? So this is basically the set of all binary words of length n, right? So set of binary words of length n, okay. Now, if you have this, then we can consider the the sequence of these numbers Wn, where n is greater than or equal to 0, right? So basically, this is basically a function from the natural numbers to the Wn's, where they are indexed by the natural number, right? So Wn is indexed by natural. So what we have here, our sequence is going to be something like sequence Wn is basically 1, comma, then 2, comma, 4, comma, right, 8, etc. Because there is exactly one empty word, there are two words of length 1, right, 0 and 1. Then we have 4 words of length 2, right, these 4. Similarly, we can continue. There is 2 raised to n words, we already know, right, of length n. So we get this sequence. So this is a counting sequence. As we said, you can also look at the permutations sequence. So permutations. So we already know that there are n factorial permutations, right, of n letters. So we can define the size to be, size of the class to be the number of elements whose permutations we are considering. So therefore, if you define it that way, then your Pn will be n factorial. Right? So the sequence Pn, right, count sequence for the permutations is going to be 0 factorial, right? Then 1 factorial, then 2 factorial, etc. etc. Right? This factorial. So this way we have counting sequences. One more example, if you want, you can look at maybe previous page itself. We can look at what is the triangulations, right? So triangulations of a polygon. Of a polygon. So what I want to say is that you have, let's say, that a polygon like this, right? Then you can triangulate in several ways. You can do it this way or this way. So the number of different triangulations. How many such triangulations are possible once you are given a fixed polygon? So let us denote by the number of number of triangles that happens to be in a triangulation to be the size of the triangulation. Okay? Size of triangulation is the number of triangles in it. So if you define it that way, what you are going to get is that let's say Tn is going to be the nth Catalan number. Okay? That is 1 by n plus 1 into 2n choose n, right? If I remember correctly. So this is something that you are going to get. So you can verify this. Take polygons of different sizes and then try to triangulate them and see like how many you are going to get, and you should be able to show that it is actually the Catalan number. Okay, so we have this. So then we have the corresponding sequence Cn, right? Sequence Tn is equal to sequence Cn, right? Where Cn is the Catalan number. Okay. Now, if you remember your calculus, you must have seen that when you studied sequences, that was mostly in connection with series. Okay. So what was series? So given a sequence n, you had a corresponding series, right? Summation a, right? Then of course in calculus you are looking at whether this kind of a series converges or not, and what are the conditions in which you can it converges, etc. But we are not really interested in convergence of these things. Okay? So what we want is to somehow encode the combinatorial data that we have into a series so that we can recover it. Now, so related to the sequences, you also have studied another thing called power series, right? So let us look at. So we are not interested in this. We are interested in what we call power series. So how did we have a power series? So power series was like summation n x raised to n and greater than right. So this was your power series. Now, if if you are looking at this coefficients as a sequence, right? Sequence an. Now, the interesting thing about power series is that if you take the coefficient of x raised to n, right, in the power series, then what you get is precisely an, the nth term, or n plus 1, starting from 0, right, in the sequence. So that is something that we are interested in. Okay, so we want to encode, for example, our counting sequences. And then we want to somehow express that as a power series. And once you have this, then so for example, if you remember, you have seen that Now, if you take the power series summation x raised to n, right, n greater than 0, this was equal to 1 by 1 minus x. Right? If you don't remember this, please go back, verify, and then try to see how you can prove this. But yeah, so this is something that we have studied. Now, suppose you have the power series which is expressed as this function. Right? If that is possible, then how do you recover, for example, an from this, right? So if you want to recover an, all you have to do is that you have to take the Taylor series expansion, right? Take the Taylor series expansion at x is equal to 0, right? Around x equal to 0. So you consider this, and then from this you can you can recover the coefficient of x raised to n, right? So now what you want to do is to somehow use our counting sequences and make power series out of them. But there is only one problem that when you look at this kind of series, you always assume that they are going to be convergent, right? So if the series is not convergent, then the analysis people does not work with such series usually, right? So then what we do is that we will say that okay, we are not so you cannot call them power series in the analytic sense. So therefore what we do is that we will call them formal power series. So formal power series in the sense that it has the form of a power series, but it may not have all the analytic properties that an calculus or analysis person is interested in. But it will still have the combinatorial properties that we want to encode, and then we can manipulate this power series. So we will in the following we will always consider series which are looking like power series, at least in the form, and then we work with them without worrying whether they are convergent or not. Okay, so to define formally, so a formal power series is an expression of this form, right? Let's say a of x is equal to summation n greater than or equal to 0 x raised to n, right? A0 plus a1x plus etc. Where the sequence an n equal to 0 to infinity is a sequence of coefficients. We will assume that the sequence is over a field k, and for most practical purposes, we will assume that k contains the set of all rational numbers. Okay. So we'll assume that we are working with a field which contains the rational numbers. So in this case, what we are going to look at only the three possible candidates first, right, which are q, then reals, and the complex numbers, right? So we will work with these three, and without really mentioning it, we will assume most of the time it is going to be R, and unless we want to use C, in which case we will make it explicit, or C or Q. But so this is our assumption. So this is a formal power series. And let us look at a couple of examples. So here is an example. F of x is equal to 1 plus 2x plus 4x square plus 8x cube. Right? So this you already saw. So this is one series. Then g of x is equal to summation n greater than or 0 n times x raised to n. We define say b of x is equal to summation n factorial x raised to n. So this is an example of a power series, right, which does not converge, right? In fact, the only point it converges is x equal to 0, right? Everywhere else, it is not going to converge. But we will still work with such series. So these are all examples of formal power series. Okay? Now, if you if you look at this series a of x is equal to summation n greater than or 0 x raised to n, you already know that it is 1 by minus x, because our series the series converges, right? We already have verified in calculus. For mod x less than 1, this converges to the function 1 by 1 minus x. So we have so we can represent this this series, power series, as this function. So in some cases it is possible, right? For the cases whenever it is converging to functions, we can represent it as a function itself. And if it is not converging, then we will write it as a series itself and work with the series. Okay. Now, so similarly, like your first example f of x, right? So what is f of x? 1 plus 2x plus 4x square. But this has an uncanny resemblance to 1 plus x square, because you just replace x with 2x. So therefore you can show that this series converges to 1 by 1 minus 2x, where the interval of convergence may be different, but it still converges, so you get a function. So the reason we are not really worried about the convergence is that we are not going to substitute for x and evaluate it at any point, right? We are going to just use this form, and then we are going to recover the combinatorial data, which are the coefficients. Okay, so before proceeding further, we want to look at a generalization of our binomial coefficients. So you remember binomial coefficients, right? We defined the binomial coefficients for positive integers n and k, right? N choose k was defined to be right, n into n minus 1 into n minus 2, etc., n minus k plus 1 divided by k factorial. We could simplify this to n factorial by k factorial to n minus k factorial. That was possible in the case of when both n and k were integers. Now, on the other hand, suppose you want to extend it to the case where n is not necessarily an integer. The first number is not necessarily an integer. So we are extending it to all the real numbers as follows. So the extension to real numbers is as follows. So a choose k is defined to be a into a minus 1 into a minus 2 into etc. a minus k plus 1 by k factorial. Exactly like the way we defined for n. But in the case of integers, we could recover, we could simplify it further. But in this case, unfortunately, we cannot do that. But it will still, be the case that whenever a happens to be integer, it will reduce to the usual binomial coefficient. So this now we can work with this. So for example, you have let's say 1 by 2 choose 3, right? What is 1 by 2 choose 3, right? It's equal to 1 by 2 into 1 by 2 minus 1, which is minus 1 by 2 into minus 1 by 2 minus 1, against minus 3 by 2 by 3 factorial, which happens to be 3 by 48, right? And then we will get 1 by 16. So so we have this generalized binomial. So we will use it. In fact, we can just see an application to prove the previous case of the power series convergence. So here is a theorem. Like you can expand, for example, the binomial series right now with real exponents. So 1 plus x whole raised to a, right? So what is 1 plus x whole raised to a? So 1 plus x whole raised to a is summation n greater than or equal to 0 a choose n x raised to n, right? That is the claim. Now why is this true, right? Where a is a real number now, right? So a belongs to R. So how do you prove this? Well, you can take it as a homework, but what all you have to do is that take the Taylor series expansion about the point x equal to 0. Then the coefficient of x raised to n by n factorial is basically fn 0, right? So you just you just verify that this fn0 happens to be a into a minus 1 into a minus 2 into etc. A minus k plus 1 or a minus n plus 1, and then you have n factorial below, right? Because when you take the Taylor's expansion, you take the derivatives, your n is going to come out. So what we want is precisely to show that this by n factorial is basically a choose n, and that and then you will get your result. Okay? So just do that. Now similarly, you want to show that 1 by 1 minus x is your power series. So basically, how do you explain 1 by 1 minus x using the binomial theorem? No, right? Because you can now write 1 minus x whole raised to minus 1. So using the binomial theorem, you will see that. So this is right. Minus 1 is a real number, and so x is just replaced by minus x. So therefore, I can now substitute it here, right? So therefore, summation n greater than 0 minus 1 to n into minus x whole raised to n. Now, what is that? That is so you have to just find out what are minus 1 choose n, right? So minus 1 choose n is equal to minus 1 into minus 1 minus 1, which is minus 2 into etc. minus n by n factorial, which is equal to minus 1 raised to n into 1 by n factorial, right? Minus 1 whole raised to n by into n factorial by n factorial, which is minus 1 whole raised to n. So so we get that. So this is basically minus 1 whole raised to n into minus x whole raised to n, which is minus 1 into minus x, which is x whole raised to n. Right? So therefore, it is summation x raised to n. So we have already a proof that summation x raised to n is equal to 1 by 1 minus x. Okay. So now, just like in the case of power series, we can define addition or subtraction or product, all this thing of formal power series. So we define it to be compatible. I think I missed something here. So this is basically summation n greater than or equal to 0 f I fn plus gn. Okay, so f plus g of x is summation n greater than 0 fn plus gn x raised to n, where f of x is summation fn x raised to n, and g of x is summation gn x raised to n. Now you can define the product, which is a convolution. So product of f and g, right? So two power series f and g is summation n greater than 0 summation I equal to 0 to n fi into gn minus I x raised to n. Now why is this defined to be the product, right? Because if you look at the the series, expanded series, and take the product and see how many ways or whichever ways you are going to get x raised to n and what are the corresponding coefficients, right? So to see this easier, we can look at this following figure, right? So you have the first series in which you have these terms f0 f1x f2 x square etc. fn x raised to n. Now if you take these terms, right, and then multiply with these terms in the second series, right, gn x raised to n, g minus 1 x raised to n minus 1 etc. Then so how we can get x raised to n, right? For example, you have to take 0 you are taking, and you need to take in the second from the second factor, you need to take x raised to n, right? X raised to n is gn, so you will get f0 and gn. Similarly, you have to take f1 and gn minus 1. Now we don't have to consider anything beyond, because when the power of x is larger than n, in the product you will never get x raised to n. So therefore, we just need to look at these terms, and you can see that only these corresponding terms are going to give you x raised to n. So therefore, that is why you get summation I equal to 0 to n fi into g n minus I. So if I will give power I, gn minus I give power n minus I. So therefore you get power x raised to n. So this is the product of power series. This is sum of power series. In fact, you can say even further. You can say that, like, the formal power series forms as a ring under these two operations, right? Addition and convolution. So we have the formal power series ring. Okay. So let us say that K is the ring of coefficients, right? In general we can define it our ring, and in our practical process we will assume this ring to be a field. In fact, which contains, like as I mentioned earlier, Q, R, or C. Now, so the ring of formal power series is denoted by whatever is field, right? Within double square bracket x. We are looking at the one variable case. So this is the ring of formal power series, which is basically equivalent to the set of infinite sequences of k, right? K raised to natural number n. Written, I think I missed the line here, right? It is the same k. The field of infinite series written as infinite sums, right? So usually what we want for our algebraic purposes is just the sequences, infinite sequences of k, but we can equally represent it as the infinite sums fn x raised to n, which is basically saying that separating out the coefficient, because what we know about the power series is that two power series are equal if and only if their corresponding coefficients are equal. The coefficients of x raised to n for every n is going to be the same. So in that case they are equal. Yeah. So with the the usual sum and product we defined earlier, right? Summation fn x raised to n plus summation gn x raised to n is summation fn plus gn x raised to n, and the product is summation n greater than or equal to 0, summation k equal to 0 to n fk into gn minus k x raised to n. So these are the products under which this forms a power series ring. Now the usual analytical properties, like if you take the exponential of the series or logarithm of the series, etc., one can show that it extends to the entire k double bracket n, double bracket x, right? The ring. Whenever it makes combinatorially, it makes sense. Okay. So we will probably come across this at the end of our course in when we look at some special topics, but till then we really don't need this. I'm just mentioning it. And if you consider your for example, if you take a field element, it's an element, let's say small a in k. Suppose I denote it by just identify this with the infinite series. Let's say a comma 0 0 etc. Identify 0. So under with this assumption, you can see that, like the usual k of x is contained in this, and the entire k double bracket x is basically have a vector space structure over the field k. So these are things which we are not going to immediately use, but to just for completion, I just mentioned it. Okay, so we can also define the derivative, and we define the derivative for formal power series in the same way, so that it coincides with the notion that we have in the analysis. So even though one can say that, like the derivative does not make sense because there is no interval in which some series that we consider are convergent. So in that case, it may not make sense in the analytic sense, but we can still consider this in the formal sense. So the formal derivative of the series is defined exactly like this. So d by dx of function x raised to n is summation n greater than or equal to 1 n fn x raised to n minus 1. So example, right? If you have summation greater than 0, n plus 1 x raised to n, show that this is equal to 1 by minus x whole square. Okay, so we give three different proofs. One is using the idea just we looked at before, right? So summation x raised to n equal to 1 by 1 minus x we already established, right? So we proved this. Now what you do is that you take the derivative on both sides, right? So differential with respect to x on both sides. So you take this. So what is this? This is by definition of the derivative. This is summation n into x raised to n minus 1. Right, that's what we just define here. And what is on the right side? The derivative 1 by 1 minus x is 1 by minus x whole square. Right? But now this is this is n greater than or equal to 1, so I get it by one point, like I can make n minus 1 to start with n. So therefore this is basically n greater than or equal to 0 and plus 1 x raised to n. So and that is basically what we want, right? That is equal to the 1 by 1 minus x square, which is the derivative of 1 by 1 minus x. So we do the differential calculus on both sides, so you get this identity. So let us prove this in a different way, right? So here what I am going to do is that we can also see that 1 by 1 minus x whole square is the product of 1 by 1 minus x in 1 by 1 minus x, right? So why don't we try that same thing, right? So a of x is equal to 1 by 1 minus x, b of x is also 1 by 1 minus x, so you take the product. So if you take the product, so a of x into b of x, right? Now we know that 1 by 1 minus x is summation x raised to n. This is again summation x raised to n, right? So what is this? By definition, this is summation n greater than 0, then summation k equal to 0 to n, right? ai into bn minus I, right? And but what is this, right? So this is ai into bn minus I is, so ai is 1, ba is 1, right? ba for every I both are 1 because the series has all the coefficients b1, right? We are looking at the sequence. The sequence, this is corresponding to the sequence 1 1 1 1, right? This corresponds to the sequence, right? So therefore all the coefficients are equal to 1. So ai into bn minus I is 1. And how many times are here? 0 to n, which is n plus 1. So therefore this is summation n greater than 0 plus 1 into x raised to n, which is what I want to prove in the first place, right? This is what we want to do. Okay. Now let us look at even one more proof using the generalized binomial coefficient. Okay. So we have 1 by 1 minus x whole square can be written as 1 minus x whole raised to minus 2, right? So now a is minus 2, x is minus x, and we have the formula, right? Minus summation n greater than 0 minus 2 choose n, right? X raised to n, right? So what is this? Minus 2 choose n. Minus 2 choose n equal to minus 2 into minus 3 into etc. minus n plus 1, right? Minus of n plus 1, right? Because you have to minus, yeah, minus. So this is a minus n plus 1, right? Yeah. So this is basically minus of n plus 1. and divided by n factorial, right? So this is equal to n plus 1 factorial by n factorial minus 1 whole h, right? By n factorial, which is basically n plus 1, right? Because n factorial cancels out. So minus 1 whole h to n plus 1, and therefore we have minus 1. This is sorry, this was minus x whole h to n, right? So this is equal to summation n greater than or equal to 0 minus 1 whole raised to n, n plus 1 into minus x whole raised to n, which is equal to summation n plus 1 x raised to n. So that is it. So we have 3 different proofs of the same identity. Okay. So now we want to solve a recurrence relation. Okay. So one of the advantages of using generating functions we have not yet defined are to solve recurrence relations. So let us start with an example. So here is the problem. So there are 5 people, so they start a new religion. So what they do is that they start wearing blue t-shirt and say that we are worshipping the blue goddess and we need to honor her by wearing blue t-shirts. Now, so every day what do they do is that so they spread the word, right? They preach the gospel to others, right? So whenever they talk to other people and then spread this word, they get interested and immediately join the religion. So that is our assumption. So they join the religion and they start wearing the blue t-shirts and they also start preaching or spreading the word. So from the next morning onwards, they will also do this. Okay. So every day, what they do is that they spread the word to others, right? Now, but of course, every day exactly one person stop believing in this because they will realize that okay, after I do this, maybe I was too quick to start doing this, so let me get out. So he will stop believing and then he throw away the t-shirt, and then do something else. Now after n days, how many people will be in the religion? So that is the question. Right? So the question is that 5 people start this every day. They go and preach each of them, right? Preach to others who will join, right? And then they will from the next morning onwards they will also start spreading this, and then again they will tell to the 2 others. They will also join, right? But every day one person out of all this thing, one person will say that I am stopping the belief, right? One person from all of them, right? Whatever is the group, just one person stop believing. Now how many people are there in the religion? So from the definition it is kind of clear that one can from our previous experience with recurrence relations, one can easily set up a recurrence relation to show how this grows, right? So let us say that an denote the number of devotees after n days. Okay? So once n days are over, how many are remaining? So that is denoted by an. So what we know about a0 is 5 because they started with 5 people. And what is a1, right? So a1 we can find out by looking at this, right? So we know that an is basically 3 into an minus 1 minus 1, right? Why? Because so we already have an minus 1 people to start with, right? So let's say that we had 5 people to start with. Then they spread to 2 others. So including them, we have 3 times that many, right? So 3 into an minus 1. But one person stopped believing, so therefore it is minus 1. So by the end of the day 1, right, you have 14 people, right? 3 into 5 minus 1. Similarly, you can verify that A2 is 41, and you can compute this also, but suppose you are asking that what is A100, then you have to calculate this for 100 steps, or if you want A2000, then you have to calculate for 2000 steps. So instead of that, can we do something easier? Or we want several of these values in between, and we don't really want the other values, right? So I want, let's say, a 20, a 100, and a 1751. How do you find this without doing all the extra work in between? So for that, we will try to encode all this data, right? So you have a sequence now, right? Natural sequence, AN, 5, 14, 41, etc. Now from the sequence, can we encode the entire sequence into one, right? So if you can do that, then you just need to find out the nth term in that, and then you will get what is something that you are looking at. So that is the idea, right? Now how do you do that? For that, we use the idea of a power series. Okay, so we define a power series, let's say a of x, which is basically the summation n greater than 0 a n into x raised to n. Okay, so which is basically 5 plus 14 into x plus 41 into x square plus etc. Right? Now, so this basically says that, okay, I have now written this as a series. So we can ask, like, what is the big deal, right? Like you have this entire series, right? Where you have these coefficients appearing there, and you have this entire series, and what else we are going to do with that? So let us go a little further. So we first define what we are doing here. So suppose you have a sequence of real numbers f0, f1, f2, etc. Then the formal power series, okay, f of x equal to fn x ratio n is called the ordinary generating function of the sequence fn. So we have the sequence fn, and what we do is that we convert this to a formal power series, right? And as we already mentioned, the formal power series represents exactly the sequence. There is no difference in fact, right? Because we are saying that, like, whatever is the coefficient of x raised to n, right, in this, that is going to be our fn. So we represent this as a formal power series, and this is called the ordinary generating function. So why I call ordinary? Because there is something is coming. So we will look at the other thing later, but for the time being, this is our ordinary generating function. Without worrying whether the series is converging to a function or not, we will call it the ordinary generating function. Now, so what we have here in this problem is that a of x is equal to summation an into x raised to n. Then we know that an is equal to 3 into an minus 1 minus 1, right? This is what we already established, recurrence relation, right? Now, we want to use this recurrence relation, which contains two unknowns, right? An and an minus 1. And then we try to write this recurrence relation in terms of one unknown, which is a of x. Right? So a of x is this entire series. I'm going to write this recurrence relation, convert this, and then write it in terms of write another equation so that I can solve at least this. So once I get a solution to this, I can hopefully find something about this. So what we do here, well, we have an is equal to 3 into an minus 1 minus 1. So I convert this to our generating function as follows. I multiply both the left side and right side by x raised to n. So I start with an x raised to n, right? Then summation n greater than 0, right? Which is equal to, again, summation. No, sorry. I think let us first write this, right, for the summation. Okay. So this is equal to 3 into an minus 1 x raised to n minus 1 into x raised to n, right? Now we know that, so here the summation starts from n minus 1, right? So an minus 1 we are looking at. So therefore we can say that summation n greater than or equal to 1 1 an x x raised to n is equal to 3 times summation n greater than or equal to 1. Or in fact, I can take 1x out. Okay, let us do that later, right? Go to 1 x raised to n minus 1 x raised to n minus summation n greater than or equal to 1 x raised to n, right? Now, so once you have this, well, so how much this is being close to a of x? So here only the first term is missing. What is the first term? We already computed, right? First term is 5, right? So therefore, I can use that fact. So this is basically a of x minus a0, which is a of x minus a0, which is 5. And this is, again, if you take one x outside, this is basically n greater than or equal to 0 n x raised to n, which is a of x, right? So this is 3 times x a of x. And this we already know. This is basically, if you take one x outside, you get 1 by 1 minus x. So this is basically x divided by 1 minus x. So we have written, this as, in terms of a of x, right? So we have converted this. Now I can write, yeah, so this is something that we already have. And then we can write, converting this to the left side, a of x, collecting them together, a of x into 1 minus 3 of x, which is the routine, equal to minus x by 1 minus x, right? Now, therefore, a of x is equal to this all divided by 1 minus 3x. So, which is 5 by 1 minus 3x minus x by 1 minus 3x into 1 minus x. So, we get this equation in terms of, in a of x in just one variable, right? So now one variable, therefore we can solve this, right? So that the idea is to try to solve this. So how do you solve this? Something like this, okay? So the first time, for example, so what we want is, to find out an. We know that an is the coefficient of x raised to n in the expansion on the right side, right? So if you want to find out an, it's basically coefficient of x raised to n in the expansion on the right side. Now, how do you expand on the right side? Well, so if you take the first term, for example, 5 by 1 minus 3x, which is basically 5 by 1 minus 3x is equal to 5 into, right, 1 by 1 minus 3x, which is summation, right? 1 by 1 minus x is summation x raised to n. So this is summation 3x whole raised to n, right? So 3 raised to n, x raised to n, right? So therefore, what is the coefficient of x raised to n? That is 5 into 3 raised to n. So coefficient, so I use this notation. If you have a function a of x, then coefficient of x raised to n in this function I write this, okay? So this says that I am looking at the coefficient of x raised to n, extracting the coefficient of x raised to n from a of x. So therefore, this value, right? So we are not looking at a of x here. We are looking at coefficient of x raised to n. This coefficient of x raised to n in this function. So that is precisely, right, this function, which is 5 into 3 raised to n. So we got one part of it, right? So we get that coefficient of x raised to n is, from here you get 5 into 3 raised to n. But of course, we have to find the remaining part from the second term. Now the second term needs a little more work, as you can see, because it's not in the form that we already know how to solve. So now we have to convert it into such a form. So for doing that, what we can do is, there are several methods you can use. So one method we will look at is a method of partial fractions. So what you do is that you write this, because we already have factoring below. So what we do is that we just write it as, let's say, some constant, let's say alpha by 1 minus 3x and another constant by 1 minus x. So alpha by 1 minus 3x plus beta by 1 minus x is equal to this term. That's what we will assume. Then we will solve for alpha and beta. So how do you do that? Okay. So let x by 1 minus 3x into 1 minus x as alpha by 1 minus x plus beta by 1 minus 3x. So then what we have? We have is that you cross multiply, so you will get alpha, right? So x is equal to alpha into 1 minus 3x, right? Plus beta into 1 minus x divided by 1 minus x into 1 minus 3x, right? Yeah, as follows. So we have alpha plus beta. So this is x is equal to alpha plus beta, right? Minus x into 3 alpha plus beta, right? Therefore, what we get is that comparing the coefficients on both sides. So alpha plus beta is equal to 0, right? Alpha plus beta is equal to 0, and 3 alpha plus beta is equal to minus 1, right? Minus 1. So therefore, what we get is that if you take this 3 alpha minus alpha, which is 2 alpha is equal to minus 1, so alpha is equal to minus 1 by 2, and therefore beta is equal to 1 by 2. So we get alpha and beta. So once we have this, we can substitute this in this equation, and then we get x by 1 minus x into 1 minus 3x is 1 by 2 into 1 by 1 minus 3x minus 1 by 2 into 1 by 1 minus x. So therefore, this is going to be 1 by 2 into this we already know, right? 1 by 1 minus 3x is summation 3 raised to n, and this is summation raised to n. So therefore, we get summation n greater than or 0, 3 raised to n minus 1 by 2 x raised to n. So from the second term, the coefficient of x raised to n is minus 3 raised to n minus 1 by 2. So therefore, coefficient of x raised to n in a of x, the whole of a of x, is equal to the first one we computed, right? Which is 5 into 3 raised to n. Then in the second term, right? Plus 3 raised. So what was the formula? Let's see. Yeah, so this is minus of x by 1 minus 3x. Yeah, so this is basically minus 3 raised to n minus 1 by 2. Okay. So this is the coefficient of x raised to n of x. So let's see that whether it is actually true by substituting for n is equal to 0, 1, 2, etc. Right? So n is equal to 0, what we have? So this will say that when n is equal to 0, we have 5 and 1 minus 1 0 by 2, which is 5. So a 0 is equal to 5. Okay. And what is when n is equal to 1, we have 5 into 3, 15 minus 3 raised to 1, 3 minus 1, 2 by 2, which is 1. So which is 14. Right? So a1 is equal to 14. A2, so A2 is 945 minus 8 by 2, 4, right, which is 41. So A3 is equal to 41, right? So our sequence is coming. So we can verify this, and then you can see that, okay, for any arbitrary n, you can get this. Now, if you want to really make sure that you have not made any mistake, one thing you can do is to use this now, right? So this is your hypothesis, and then you can use induction, right? So take this as a hypothesis, and then use induction to prove the recurrence relation, right? So you have the initial conditions, then you have the induction hypothesis, and then apply induction. So I suggest that you go home, take this, and do it as an exercise to show that this is actually the correct value by applying the applying the induction and show that the recurrence relation with the initial conditions actually lead to this. So this satisfies this number. Okay, so that is one way to do this. Now let us look at a slightly different version. Suppose same question with a slight twist. Okay, so suppose our 5 derivatives, right, of the blue goddess are there, but now they look at a different scenario. They are more following a different protocol. So what they do is that they preach to one new recruit, right, on the first day, and who immediately joins. Okay. So the first day they are very relaxed. So they will say that, okay, this is the first day. Let us not hurry. We just take each of them. We'll go to one person and then recruit him. Now each devotee from his second morning, right? So once you join the second day, right? So what he do is that so second morning, right? Which means that the first morning is the day one for him. Okay, so if I join today evening, then tomorrow morning is my first day, right? And then next day onwards, it is my second day, right? So for each devotee from his second morning onwards, recruits 9 others. On the first day, right? After the recruitment, he only preaches to one person, but second day onwards, he preaches to 9 others. So now all of them join, and they are going to be always the devotees. Once you join, there is no escape. Okay? So you are stuck with that. So they basically do this strategy. Now, question is that how many devotees are there in the religion after the nth day? So the difference from the previous one is that, like, so in the previous one, people who join, one of them will remain, leave every day, right? And every day they had the same pace, right? You convert exactly 5 people. I mean, 2 more people. But now, first day you only do 1, but second day onwards you are in high gear, convert 9 others. Now, how do you form the recurrence relation here? So, can you think about the recurrence relation for this? So you think about this. I will continue in the next class.